Hello everyone. Let's discuss quantum mechanical model of atom. We know the dual behavior of matter by the equation of de Broglie, which can be explained as E equal to hν or E equal to mc square. So when we equate these two equations, we have hc by lambda equal to mc square, where c is the velocity of light. If we consider the velocity of any matter, then we can write it as v. Now calculate it. 1 by lambda, or we can write it like lambda equal to h by mc. mc is, we know that m into mass into velocity is equal to momentum. So here lambda is equal to h by p, calculated by de Broglie. Another scientist, Schrodinger's Schrodinger equation. Just remember this equation. There is no need to go in detail for this equation, because the solution of this equation is very complex. He differentiated. According to the Schrodinger, there are three coordinates where atom can be found. So according to the three coordinates, he gave an equation. For x it is del square x by del x plus del square y by del y plus del square z by del z. Means these three are the three coordinates where x square, y square and z square. Three coordinates x, y and z. Electrons can be found on this coordinate. If it is x, y and z, electrons can be found on this coordinate or this coordinate. The total equation given by Schrodinger is this plus 8 pi square m by h square. E means total energy, minus V means potential equal to 0. Potential energy is equal to 0. This is the Schrodinger's equation. Just remember this equation. And here is a phi. This is called psi. This sign is called psi. This psi is for wave function. For wave function, you can use the wave equations like y equal to a sine omega t, where y is displacement. By solving these Schrodinger's equation, we can equate exact energy, momentum, exact energy of any atoms. Here, psi is called wave function. X, Y, Z are three coordinates where electrons can be found, and m is mass of the electron, h is Planck's constant, E is total energy, and V is potential. V is potential energy. By equating these all, we can write this equation as given by Hamiltonian. This is Hamiltonian psi equal to E psi. Hamiltonian wave function is equal to total wave function. Total energy can be calculated by this type. Now, what is the significance of psi? Psi has no physical meaning. There is no physical significance of psi. Significance of psi. There is no physical meaning of psi. Meaning of it. It is wave function it is wave function. And now significance of psi square, psi bar square. This indicates psi square indicates it represents or it indicates the maximum probability of finding electrons. By calculating psi square, we know about the orbitals. That we can say that psi square represents orbitals. Different region where there is the probability of finding electron is maximum is called orbitals. So psi square represents orbital. We can simply say that psi square represents orbitals. So let's start with the different types of orbitals and their orientation, their shapes, and what they indicates. First, what is orbital? It is the maximum probability. Or we can say that the maximum probability of finding electron along three coordinates finding electrons along three coordinates. It indicates the three-dimensional shape of where electrons can be found along three coordinates. We can say as x, y, z. Along three coordinates in a three-dimensional system. So this is the maximum probability. If it is nucleus, this after nucleus, the space around the nucleus is called extranuclear region. In the extranuclear region, where there is the probability of finding electrons, if we have probability like this, density of electron in this region, at any place we can find the electron, but after that there is another region like this, and this is the three-dimensional structure. This is not the two-dimensional. We can only see the two-dimension, but it is three-dimensional, like a sphere. So this is the node where there is no probability, or we can say that zero probability of finding electrons. This is called nodes. This type, after nuclear region, another cell is formed. These orbitals. These orbitals are, first we can, according to the Gates board, we use shell for this type of region, and this is node where there is no electrons can be found. So there are different shapes of orbital. First orbital present is S, or subshell. We know that SPDF are different subshells, and in that subshells there are three-dimensional structures which we call orbitals. So there is types of orbital. There are four types of orbital. As you know that there are four types of orbital. SPDF, but SPDF, GH type of orbitals can be found. The different regions where there is finding of we can find the electrons are the orbitals. So here we can conclude S orbital. It is spherical in shape. S orbital is spherical in shape. P orbital, if it is X, Y, Z, this is spherical. So the shape of the S orbital is spherical. For P orbital, this P orbital is at three coordinates r. It is dumbbell-like shape. If it is X and Y, then this X along the X-axis and along the Y-axis, there is the probability of finding electron. So this type of orbital, and this is Z-axis. Probability of finding electron in X, Y and Z coordinates. So there are three types of P orbital: Px, Py and Pz. Three types. For Px, if it is X and Y, the finding of electron along the Px, so it is Px. Along the X, so it is Px. X and Y. Then finding of electrons along the Py is this Py. And if it is X, Y and Z, then finding of electrons along the z axis, so it is pz. And these two orbitals are degenerate orbitals. Their energies are same. And here, this is the node. This is the node where there is no probability of finding electrons. This is the node for px, this is the node for py, and this is the node for pz. We will discuss in later. Next is d orbital. D orbital. D orbital, the shape of d orbital is, it is double dumbbell. Double dumbbell, but not along the axis. It is between the axis. Px orbitals, all px orbitals are along the axis, but some d orbital, it is between the axis and some is along the axis. If there is no electrical and magnetic field, d orbitals are also degenerate orbitals. But when electrical and magnetic field are present, electrical or magnetic field are present, then there is a splitting of d orbitals and it becomes, it is otherwise that it is degenerate, its energies are same. So the shape of the d orbitals are this double dumbbell, like if it is dxy, this is x and this is y, then this between the axis, it becomes like this. Between x axis one dumbbell and between y axis double dumbbell. So this orbital is of double dumbbell shape like this. xy for xy coordinate, for xz coordinate. If it is xz coordinate, then it is like this, like this. This is dxz. And next is, if it is y and it is z, then it is dyz. This is dxz. This is x and this is z. Xz, this is yz. dxy, dxz and dyz. And there are also two types of d orbitals. There are 5 orbitals present here. This is according to the quantum numbers. We will discuss later. So xy, xz and yz. Now between the axis, x and y, this is between the axis and along the axis. This type of orbital is like this, along the x-axis and then along the y-axis. So this orbital is called dx square minus y square. And fifth type is dz square. There is a ring like this. This is dz square. dz square orbital. So d orbital is of 5 types. Say p orbital. There are three types of p orbital: px, py and pz. D orbital, there are five types of d orbitals: dxy, dxz, dyz, dx square y square and dz square. And according to the rules, or we can say that according to the quantum numbers, each orbital px, py, pz or s orbital means only one type of s orbital, that is s orbital only. So each orbital contains 2 electrons. Next is f orbital, and f orbital have a complex structure. F orbital, some are diffuse, some are, so we are not going to discuss the f orbital here. There is a complex structure of f orbital. So there are 4 types of f orbital: g orbital, h orbital. There are many types of orbitals and their shapes are quite complex. Next is quantum number. Before going to the quantum number, next is quantum number. We'll discuss later.